.7 Volumes of revolution. If we have an area under a curve and we rotate that area around the x-axis, we're going to create a three-dimensional object, and we want to calculate the volume of this three-dimensional object that we've created. This is also called solids of revolution because a solid is created. So really it should be volumes of solids that's created by one revolution of the area under a function. But that title's too long, so volumes of revolution it is. We're going to rotate the area under y equals 3 about the x-axis, and in this course it will always be around the x-axis. What's the volume of the solid that's created? So you can see that if we rotate this rectangle here, we're going to create a cylinder. And this cylinder is going to have a radius of 3 and a height of 1. Now we know the volume of a cylinder is pi r squared h, so the volume of this cylinder that we've created is pi 3 squared times 1, so that would be 9 pi units cubed. Rotate the area under y equals negative x plus 3 around the x-axis. When we do that, we're going to create a cone. And we want to find the volume of this cone. And we know the volume of a cone is 1/3 pi r squared h. So we can find the volume. 1/3 pi, the radius is 3. And the height of this cone is also 3. And this would be 9 pi units cubed. Now we want to rotate the area under y equals x squared from x equals 0 to x equals 2 around the x-axis. And when we do that, we create this cone-like shape, but it's got curved lateral sides. So we don't have a formula to find the volume of this shape. So we need another formula to work with these unconventional objects, because you can imagine how many different objects we can create by rotating various functions around. So it's going to look just like our development of integrals. We're going to chop the pieces up in between some upper and lower bound a and b, and we're going to chop it up into n pieces. So each delta x here will be b, the upper limit, minus the lower limit divided by n. Then the right end point of each cylinder, and we could use the left or the middle, but we could use the right just as well. When these get infinitely thin, it won't matter. But each x value here is going to be the starting value plus any number of delta x's to get each point along the curve. And it's like we're going to break this object up into disks or small cylinders. The volume of each cylinder is pi r squared h, and each radius is going to be the function at this value xi. And it's radius squared, so it's the function squared. And the height is going to be delta x. And just like for integration, we said we wanted the limit as n goes to infinity, and we want to add up all of these cylinders here. And using the same logic as we used for integration, this turns into an integral. The pi is just a constant, so it's often left outside here. The function is squared, and this infinitely thin slice becomes our dx. Now let's try this formula on the question above. We would have our volume is equal to pi. We're going to integrate from 0 to 2. And here's our function x squared, and we need to square it. And we just leave pi here until we're done our integration. So we're trying to integrate x to the power of 4. Now the antiderivative of x to the power of 4 is x to the power of 5 over 5. And we need to evaluate it at 2 and 0. So when we evaluate it at 2, it's 2 to the power of 5 over 5. And when we evaluate it at 0, it's just 0. So this is going to be 32 pi over 5, and that would be units cubed. Let's go back and try example 2 using integration. We've got our volume is equal to pi. We're going to integrate from 0 to 3, negative x plus 3 squared. We'll leave the pi in front as a constant and find the antiderivative of that. It would be negative x plus 3 to the power of 3 over 3. And we need to evaluate that at 0 to 3. So our first one, when we put in 3, is actually going to be 0. And then we've got a minus, so this will be plus 0 plus 3 cubed over 3. And that would be pi, this will be 0 plus 27 over 3. That would give us 9 pi units cubed, just like we had before. We can also redo our example 1 using integration. So we have volume is equal to pi, and we're going to integrate from 0 to 1. And our function is really easy. It's just a 3. So it'll be 3 squared in our integrand. I'm going to take the antiderivative of 9, which would be 9x, and evaluate it at 0 and 1. So when we evaluate it at 1, we'll get 9. When we evaluate it at 0, we just get 0. So this will just equal 9 pi units cubed, just like we had before. Find the volume of the solid that's generated when we rotate the region between y equals cos x and y equals sin x around the x-axis from x equals 0 to pi over 4. First thing we need to determine is which function is on the top and which function is on the bottom graphically. So we can just remember from trig that cos starts at a maximum, sin starts at its midline, so cos would be the one that's on top. Now we're going to find the volume under y equals cos x, and then subtract the volume made by rotating the area under y equals sin x. So we have to do those two things separately. That's why it says here, square individual functions first before subtracting them. If you subtract them first, then you'll get something else and be rotating something else around the x-axis and make a completely different shape. So for ours, we want volume is equal to pi, and we're going from 0 to pi over 4, and the one that's on top here is cos. So we'll do cos squared x, and then we need to subtract the area made by the sine function. So sine squared x dx. Now that we've squared them individually, now we can actually put these two integrals together because they have the same upper and lower bounds. So I'll say cos squared x minus sine squared x dx. Now I know that this is an identity, so I'm going to make that substitution, and this would be cos 2x because that will be easy to integrate. And now I'll find the antiderivative of cos 2x, and it would be sine 2x, and we need to divide by 2. We need to evaluate that from 0 to pi over 4. Pi, and we'll put pi over 4 in here, so we get sine pi over 4 times 2 is just pi over 2, and then minus sine at 0 times 2 is just 0, and that's ultimately just going to be 0 there, so we can cross that out. and we get sine pi over 2, and that's 1. So we got pi times 1/2. So we just have pi over 2 units cubed. In this example, we want to find the volume of the solid that's made when we rotate the area in between x cubed and x squared around the x-axis. Now you see that something interesting is going on here. Initially, x squared is the greater function, and then after x equals 1, x cubed is the greater function. So we have to do this volume in two separate integrals, from 0 to 1 and then from 1 to 2. Because from 0 to 1, x squared is the higher function, so it needs to be first, and then we will subtract x cubed from that. And then for the second volume, we have from 1 to 2. The x cubed function is the higher one, so we need its volume first, and then we'll subtract the smaller volume that's made by x squared. So let's clean up these integrands. So from 0 to 1, we have x to the power 4 and x to the power 6. And then this one, the x to the power 6 minus x to the power 4. And we'll take the antiderivative. So this will be x to the power 5 over 5. And this one will be x to the power 7 over 7. Evaluated from 0 to 1. We've got pi, x to the power 7 over 7, minus x to the power 5 over 5, evaluated from 1 to 2. Now pi is the coefficient for both of these. We've got 1 over 5 minus 1 over 7, and then when we put in the 0, it just equals 0, so we don't need to write that. For the next one here, we've got 2 to the power 7, so that's 128 over 7, minus 32 over 5, and then minus 1 over 7, and then minus a negative, so that would be plus 1 over 5. And since all these have a pi as their coefficient, we can just add them all together. So we got 1/5, and minus 32/5. So that would leave us with negative 30/5. Then we got negative 1/7, another one, negative 2/7, plus 128, so plus 126/7. We can simplify this further, so this first part is negative 6, and this second part is 18. And so we got 18 minus 6, and that would be 12 pi units cubed. Hopefully you can calculate the volume of a solid created by rotating the functions around the x-axis. Here's some questions from the textbook. Give them a try. See if you know what you're doing.